welcome to Quantum Kinetics First Diffusion Season 4, Episode 2. I'm here with
Jason MacCoy.
Jason, it's good to have you on the show once again. What are we going to be talking about today?
Well, we got a heavy show today.
Ooh.
No pun intended there. We're going to talk about black holes.
Oh, my favorite.
We're going to talk about Alan Turing.
I don't know who that is.
And we're going to answer some interesting viewer questions.
Okay, so let's go ahead and start with the question of the day, which comes from Wade Man 15.
Okay.
And he asks, could you please wax poetically on the golden ratio and how it relates to this technology?
Well, the golden ratio is a mathematical ratio. It's 1.618.
Okay.
And I don't know why I know that one cold of all the ratios and all the things, because the golden ratio is a special ratio that is in everything in nature.
Okay.
And in processes like the spiral of a black hole, the shape of a nautilus shell, like a shell from a sea creature. It's in our faces.
No way.
It's in our bones, the length of our bones, the way our fingers can bend in on themselves. There are these ratios between this joint, this joint, this joint, and this joint, and your forearm, and it goes all the way through your body.
Isn't it in plants too?
It's in plants. It's in physics effects, and of course, related to the way it, is perhaps part of the quantum kinetic well, is like we talked about when we talked about Victor Schauberger.
Oh yes, Victor Schauberger is the swirl master.
The swirl master, and that. Well, it's actually part of music too. That horn shape that is created in the graph is also created in Victor Schauberger's spiral, the spiral that goes down. And I imagine it must be part of how the quantum kinetic well pulls atoms together.
Well, the quantum kinetic well is essentially a synthetic gravitational flux induced from a very unique type of electricity that comes from the arc reactor fusion on demand.
Wait, say that again. A what?
Oh, essentially the quantum kinetic well is a synthetic type of gravity electrically induced by the arc reactor fusion on demand. It's like Bob Lazar's idea of the emitter, and Bob Lazar is like a ufologist type of person that worked at Area 51 allegedly, but he talks about how the gravity amplifiers emit this type of gravitational wave. It's a wave.
Okay.
And so going back to the Fibonacci spiral, what's the deal with the numbers? Like, can we learn something about the numbers, like with numbered notes and music theory? What about numbers and Fibonacci gives us a code key clearance to something?
Absolutely. Yes. And I love the number stuff because
that's your thing.
It is my thing. And Pythagoras said the whole world is numbers. And I kind of do see it everywhere in every way. There is a numerical way about it. But the thing that's so interesting about the Fibonacci series is that one number begets the next number, begets the next number. So you can, when you look at one number a ways out, you can tell something about the number that came before it.
Okay.
And then the number that became before it, because they're all related by this ratio.
Okay. And the ratio, so I remember watching Disney movies way back in like the 80s when I was a kid, and they had like the Fibonacci spirals and then the numbers and the flower petals would like grow. And it was like what about that phi, is it? Is it phi?
Yeah, phi.
That number, 1.618. What about that is so powerful? Why is it that powerful?
Well, because there's a whole bunch of reasons, but one of the main reasons and one of the main interesting things about it is that it's based on a series of numbers, so that you can tell something about the number before it by the number you're currently on, and you can tell something about the number after it by the number you're currently on.
So if I'm understanding this, it's almost as if it's a code that you have to follow, that the nature says this is the code to follow in order to make the next right step. Like almost like a code hack. If you follow this code hack, which we'll talk about the Enigma machine.
Yeah.
Which
Alan Turing,
relates right into that.
Yeah.
I don't know much about Alan Turing, but I do know a little bit about the Enigma machine itself.
Yeah.
So the code of the universe is almost like the key to get into the door of free energy, maybe?
Yeah, I mean, that's this is a side note on phi and the Fibonacci series and all of that stuff. The symbols that are part of this, I'm not going to go too deep on sacred geometry.
Hey, we're talking about black holes today. We're going to go a little deep about
something. We're going
something.
deep. We're going heavy on all this stuff. It's the symbols, the symbols. So when my first video game I worked on was all about ancient civilizations.
Okay.
And
Which is at Sierra.
This is at Sierra. Yeah. Okay. This one of my first video game jobs. It was awesome because we got to study the ancient civilizations and the symbols that they used. And I just became fascinated with why these symbols. Why is it that this civilization emphasized this particular symbol over and over again? What is it about that symbol? And it turns out that the symbols embed mathematically these ratios inside of them. That's why they are that symbol. That's why it's a star, why it's the what is it called? Piscis or
Vescapisces?
Yeah, we'll
Pisces, Pisces.
Can Iron Man show that one on the?
Yeah, it's just basically Vescapisces is like an interlocking double circle type thing. And actually, the double circle locking.
Yeah.
You showed me last week a bit from Joe Rogan about the photon entanglement made the what is that yin yang? Symbol.
Yin, yang,
And they were using some type of quantum microscope to see when but photons are entangled in a superposition state, which means on and off at the same time. It created that yin and yang symbol.
Amazing.
And is the Fibonacci spiral kind of in the yin and yang thing?
Yeah, I believe it is.
I think it is too.
And there's this, we'll hit the B-roll on that, but there are, when you look at sacred geometry and all these different symbols and diagrams, even the Christian cross and even symbols from many, many other religions or philosophies, I was getting too into it there.
Let me talk about the symbols. I'm getting excited.
So they have all these symbols basically have this stuff in them. That's why they are the way they are. So the Fibonacci series is kind of unique because it gives you this sort of like almost like historical record. And I think you were telling me earlier how that you were thinking about that in terms of like the people that have come before us in this trajectory of science and innovation. And
well, like the idea of like AI is a processing information system that grabs information and then compiles it into a pipeline or a well. Like you type in pretty girl dancing, in a mosh pit. And it pulls information from meta tags to create this thing as information and pulls it in and then coagulates it into the image you want.
Right.
And the mathematics of processing information, which is what the computer does in general, zeros and ones. That's just a normal computer. But what if you can create a situation where it's on and off zeros and ones and zeros and ones, and it makes a symbol, like it actually makes a Fibonacci sequence for you to follow. Like it's as if when you put the electron in a state of superposition, aka resonance with like the arc reactor technology, it creates the answer for you. The code key is shown, and then you get to point it where you want it to go, or you get to put it at something like rad waste. I want to clean this, solve this for me. And it just solves it. It disintegrates the uranium. It creates the hydrogen and oxygen from water into a heavier element. It just creates an iron oxide material that's carbon-based to cool down the radioactive waste.
Right.
And so the code, the Enigma code, is the resonance, I think.
Well, that gets into Alan Turing stuff.
Let's go for it.
Since you mentioned the Enigma code,
let's do it.
Part of it. So Alan Turing was a mathematician in World War II, British. And he and several other mathematicians worked on breaking the Nazis' Enigma machine, which basically encrypted and encoded their messages. So they could have had a military message saying, hey, we're going to blow up this boat, or we're going to control this waterway. And they would type it out into this.
The Enigma machine. It was like a typewriter.
Yeah. The Enigma machine's a typewriter, but it changed the way that the letters came out. So if you were on the other side, you got this jumbled message.
Yeah.
If you intercepted that jumbled message, you didn't know what to do with it unless you could decode it.
Because you have to have the key code to
Right.
fit into the software. Basically, it was like a hardware machine computer
Right.
that had these dials that would click every time you hit it. It would
Right.
move.
Right.
It was like a clock,
Yeah.
but it was also like a typewriter clock,
Right.
which is interesting because time kind of played into every time you key it, it would move one. It would move one.
Right.
So there was a sequence to the time rate of when, and you had to set the code right. Then you could type your message.
Yeah.
And everyone that was given the code knew what was going on, but anyone who didn't have the code wouldn't know what was going on.
Right. They had the machine to decrypt it. And that, I guess, perhaps where we're going with this is that the universe has these coded ways of working, coded messages,
Gravity.
and we can decode them, which is scientific experiment or
Observation.
observation. Right. Yeah.
Yeah. And so the code for the Enigma machine, how did Alan Turing
Yeah.
crack that code? I always mess that up. I always see Turing, but it's
all right.
Turing.
It's all good.
How did he crack the code?
Well, he and I think it's appropriate to say many other people, including the Polish, who did a lot of work on previous versions of it.
Sure.
And so this cat and mouse game of encryption has been going on, and I'm sure it's still going on.
Even right now.
Amazing.
Even right now.
That gets into another.
VPNs.
Yeah. And they're talking about quantum and encoding stuff in a quantum state so that if you look at it, it changes it, and then it lets somebody on the other side know it's been analyzed.
Yeah, man.
That's
quantum computers, baby.
That's a bigger thing. But I think the thing that Alan Turing did, which was so amazing, is he created this machine. I think it was Bob is what they ended up calling it.
It was huge, right? It
Yeah.
was, it was like almost a wall.
Yes, it was like a giant refrigerator unit. But there was many of them, by the way. Later in the war, they had many of them in different spots, and they were running 24/7. And there was whole teams of people, almost like a racetrack team, that kept this thing going to basically take incoming messages and try to crack them, basically.
And what was the total, I know it was probably like a huge number, to try to figure that out. What was the one thing that the Germans messed up on? Do you know what
I
that
do,
is?
yeah. There's a couple things that they did. And, you could understand how it would seem like a good idea at the time. But what they did, one of the things they did is if you had an encoded letter, like the letter A, and the machine, no matter what, would always change that letter.
To like a G.
To something else.
Or a Z.
Yes. Or whatever letters are in the German alphabet, probably. And the interesting thing about that is that one thing, because it never was that letter. If it was a letter A, it would never be letter A. So that in a way that gave the people trying to crack the code a hint that no matter what, it's not that letter.
It's as if they were so afraid, the Germans were so afraid of someone cracking their code, they never allowed the real message to be actually that letter.
Yeah. I think, you know this from like an inventor. Sometimes we get in these lines of thinking where we have to change everything or everything needs treatment. Mm-hmm. And then but in hindsight, and there was a couple other things that they did that the code crackers were able to lock onto, formats. Yeah. Like you might put a date in there, or they ended many of their messages with Heil Hitler like as a sign off. And so that gave them
a giveaway though, isn't it? It's like why would you make something so repetitive?
The oversight, and eventually it's interesting that some of those things that they did for the reason of encryption actually became the very thing that allowed that to be broken.
Well, if you take what the Germans did with the Enigma machine and take that into the Fibonacci spiral, they just couldn't get away from the idea of saluting him.
Exactly.
Right? And so that's kind of like the secret to the Fibonacci is it's always a reference upon something else, right?
Yeah.
And so if you can spot the patterns in the sequence, and though there's 100 million derivations possible here, this Enigma machine, or cracking the code of nuclear fusion, but there's patterns.
Yeah.
And so these patterns And there was a lady on LinkedIn that I forget her name. She posted something about AI.
Okay.
And she said that the Fibonacci spiral, like you mentioned, is based on numbers before it, sets before it, right?
Yeah.
That give it the kind of the guidance for the next number.
You add them just to address what it is. Like, so it's 1 + 1 is 2. 2 + 1 is 3. 3 + 2 is 5. 5 + 3 is 8. 8 + 5 is 13. 13
and so
plus,
on.
yeah, and so on.
And so on.
Yeah.
And so what this means for us as human beings on planet Earth, when you see a flower, when you see the arc reactor, when you see a beautiful face, or you see anyone's face, every one of us has the code in us, which is amazing in itself. And what I'm trying to get at is that, like, what we're doing here on this podcast is what we're trying to let you guys know, that we are taking a step forward in time with a new tech, that we give appreciation to the old numbers. Richard Feynman, Niels Bohr, Oliver Heaviside, James Clerk Maxwell, Stanley Meyer, all these people. Like, we want to give them all credit because the step that we're taking is part of the sequence.
Don't forget Victor Schauberger.
And, of course, Victor Schauberger.
Our new best friend around this place. I mean, he's the swirl master.
He's the Fibonacci swirl master, right?
Yeah.
And to go to the swirl masters is black holes. Let's go ahead and start talking a little bit about black holes now.
Sure.
And one of the big problems with black holes, they're kind of an enigma machine in themselves, right? No one really understands them. We can see them, we can observe them to some degree, but we don't know how to make them work on planet Earth. And I'm telling you, once we figure that out, we're going to be doing cold nuclear fusion all day long, and maybe even have anti-gravity craft, which some of you have mentioned in your comments, which, by the way, go ahead and like, share, and subscribe and comment. The black hole is an enigma machine to science today because it doesn't really work with classical physics. It does to some degree, and it doesn't really work all that well with quantum physics, but it does to a degree, but they don't link. So the black hole seems to be this empty link of knowledge between classical physics and quantum field theory. We're trying to find the unified theory.
Yeah.
And it's in a black hole. I'm telling you, the secret is there.
Okay, so black holes, obviously, big topic, right? And the implications of them, and if we could create one on Earth, and if we can use what is going on in a black hole to do stuff that we want to do, that would be amazing. Let's just start with the basics of what a black hole is.
A black hole is a thing that has an immense amount of gravity, that it has so much gravity, because we know that when there's gravity, the light will bend. Electromagnetic radiation will bend around something, right?
Okay.
It's like if I have this thing, and this is a black hole, it will bend around it, okay? And the reason it's black is because no light can get out.
Everything's getting sucked into the middle of it, right?
Yeah, into this void space.
Okay.
But there's something massively heavy in there that's causing the light to not escape. So the atmosphere of a black hole is black. Like, for example, there's a quote that says, "Nobody can hear you scream in the emptiness of space, just like nobody can see you as you enter a black hole. You disappear."
So just the logistics of what the black hole is. So is it a giant, is it a planet that's super crazy heavy, or is it just a grain of sand in the middle of that that's super crazy heavy?
We don't actually know, Jason. Nobody really knows what's actually inside a black hole. Nobody knows. No one's been there.
I mean, of course.
I've never taken a detector and gone in there.
Never taken a vacation to the center of a black hole and seen how that goes.
It would be like taking a long nap.
Yeah.
And like a quiet nap.
By the way, you just said long nap, which made me think about some of the other crazy stuff that happens with black holes, which is time dilation. Mm-hmm. So this is, we're getting, I mean, I'm way over my skis on this one, so to speak, with the physics of it. So my understanding of a black hole is it's super heavy. There's a thing called a
event horizon
where light can't get out.
Right.
And then you mentioned there's something else special that happens at that event horizon.
At the event horizon.
But wait a minute. Also,
okay, go ahead. Keep going.
Also, time. This is the craziest thing about it. Time slows down around a heavy black hole. Mm-hmm. Time slows around heavy stuff. Okay, so then we have time dilation we have an event horizon. You mentioned that on that horizon, there's energy that comes, it's getting split, basically.
Yes. So in the emptiness of space, where there's no gravity, there's these thing called positron-electron pairs, and they're popping in and out of existence all the time. It's called a Dirac sea.
Okay.
It's where an electron and a positron are like popping in and out of existence. Think of it like the breath of God. It's this potential creational force that is always there, and it has a huge amount of energy density, but it doesn't actually make any mass until an electron actually pops into existence and is stabilized. And now you have an electron that's stable in a resonant orbit, like a tune, like when you do an octave, dong, and then all the waves ride on each other, and now it's there. It's a note. Multiple notes, though, in a way. And so when this positron-electron pair production is vibrating and it gets close to a black hole, it's so crazy, is that the electron and the positron are torn away from each other. Okay, and so the electron falls into the event horizon to never come out again. And then what comes out of the black hole is a positron.
Is that like an antimatter positron?
Yes,
positron?
It's an antimatter particle.
Okay.
They call it virtual particles.
Okay.
But it's an antimatter particle.
And it's always the positron.
And it's a positive charge. So it's being repelled like two magnets, right? If you have positive and negative, it clicks together, right? So whatever is inside the black hole, Jason, is positive because it's sucking electrons in.
Oh, and it's pushing
and it's pushing the positron away.
Is that Hawking radiation?
And that's what Hawking radiation is. So whatever's inside the black hole is positively charged. We know that. That's all we know.
The deduction there, it's easier. It's not so easy to say. By the way, shout out to the margaritas. Strawberries,
there
right?
you go. Hey,
cheers.
Season 4, longest nuclear fusion podcast in the world. Thank you, Jason.
Yeah.
And we're just started, man.
It's an amazing. I remember. I mean, this is a sidetrack
time warp.
Time warp on the sidetrack with a derail. I remember when we were almost at 100,000 subscribers, and I had this whole thing I was going to say to you about, we just got to tough it out. We just got to get to 100,000. That was like by the time
6 months, 8 months ago.
By the time I caught up with you for that conversation, we were at like 160. I mean, it just has been going light speed. There you go. We can talk about that.
Yeah, we're like a black hole. We suck in everyone.
By the way, negative light is a thing I got to ask you about, because that is something you've mentioned that several times. Okay, let's talk about negative light just while we're jumping around here. So when we turn on a light bulb, okay, I'm just thinking about the way everybody thinks about it, right? Yeah. When you turn on a light bulb, that light, my understanding is that the filament in the light bulb heats up, then that excited energy basically gets radiated out in a
positive light.
And that's it. That's all. I mean, that's what most people think about light, myself included. What's up with negative light? How is that even possible? What is that, and how is it possible?
Oh, great question. Okay, so on an oscilloscope and electricity, there is a way to create a biased waveform. So let's just say you have an AC wave that starts at 0 reference and it goes up and it goes to 0 and then goes down and then back to 0.
First of all, wait, hold on. AC, what's that?
An alternating current.
Okay.
So it's electromagnetic radiation is in a magnetic field going like this and an E field going like this. It's a crisscrossing.
Gotcha.
But they always go along the 0 axis, like up, down, up, down. They always have 0 reference, okay? Just like electronics and all that. There is a way in physics and electronics to create a biased waveform of light, or electricity for that matter, where you can have the AC wave stays an AC wave, but you can bias it down below the 0 reference. It's still an AC wave, same frequency, same amplitude, everything stays the same, but it goes down. Or you can have it go up above 0 reference. So this phenomenon in electronics called biased transformers can be used using the arc reactor to create more negative light or create more positive light, repulsor technology. So this is how Iron Man's technology works for flight, is you create these unique electrical phenomenon like a black hole. Or, Jason, did you know that there's a white hole? You ever heard of that?
I have heard of it.
White hole?
I don't know if I'm ready to go there yet. I'm
No.
like, I don't know if I'm ready to. My understanding of a white hole is like a black hole sucks everything in and a white hole just emits everything all the time.
Sounds
But
like a star.
it does sound like a star. Is it not a star?
It is a star.
Okay.
It's that simple.
Is it a jacked up star? Is it like a superpowered star? Or?
So if you look at the picture here of the black hole, you can see that the atmosphere looks black. That atmosphere is the absence of light escaping.
Right.
There's stuff going into it, but it's not escaping.
A super
That's an
dense
atmosphere.
bubble of
Atmosphere.
black hole atmosphere.
And when you look at, like, say, the sun's atmosphere is on fire. Not the planets or not the core substance of mass. The mass of a star is black and cold, by the way. Because when you have a magnetic solar, what do they call those, solar flares or those sunspots that like make a void in the atmosphere, you look down into it, it's black, just like a black hole. It's got the same effect of a gravitational flux. It's so intense that nothing can really get out of there. But it's the coronosphere, it's the photosphere, it's the outer atmosphere that's on fire. It's literally on fire. And plasma. It's plasma fire together. But because the gravity's not strong enough at a star level versus a black hole level, the black hole has so much gravity it can't even ignite. There's not enough situation of criticality of terms of the quantum and the classical realm to ignite the flame of thermonuclear burning. But in enough gravity, and this is what's so interesting about the Fibonacci spiral, is that the Fibonacci spiral has number sets, and when you get to a certain number set, that gives you a certain amount of, like for example, if I take this ball and I grab one of the strings, you see how long that is? Now, check this out. If I grab 2 or 3, it doesn't even go down very far at all.
Right.
If I grab a whole bunch of them, it won't go down at all. And so the gravity, whatever the value is of the stretchiness, the oscillation effect, that determines how that black body radiator or that object is going to behave, kind of like a human, in a way.
What way? How is that? How does a black hole and a human come together? What's up?
So, great transition to the information paradox of a black hole. When electrons fall into the event horizon and get sucked in, and it emits a positron, the information paradox is torn. The quantum entanglement is lost between those two particles.
That is a circumstance that can undo quantum entanglement?
Bingo. It's one of the only ones, actually.
That's interesting, because I'm always finding quantum entanglement super interesting.
Yeah, because you can entangle a particle that's light years away right in front of you. If you can do that, you can do that. But how come in a black hole it's lost? And if it's lost, where does it go?
It rips it. It rips the bond.
It rips the bond, but where does it go?
Where does what go?
The electron, which is, by the way, electron has all potential light in it.
Well, you were saying the electron gets sucked into the black hole because it's positive, and the positron gets emitted,
flicked off,
aka Hawking radiation.
Bingo.
Now those positrons are positive antimatter, right?
It's positively charged electron matter. That's going backwards in time.
Away from the black hole?
Yes.
What the?
Yeah, so here's the thing. When you get close to a black hole, time starts to slow down.
Right.
We know that for a fact. It's not disputable.
Well, we know when we get around heavy things, time slows down, and we get away from heavy things. Okay, all right, so.
That's non-disputable, right?
Time
we all
slows
agree.
down.
And this is where, this is the whole point of the episode, is that we're going to make a postulate jump and ask you guys.
Okay, here we go. Let's do it.
Okay. When you get next to a black hole and you start slowing down in time and time dilation, all this stuff, mass correlation changes, and things start to slow down. The clock goes click, 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 click. It starts to slow down. The question is, for the audience, if you can slow down time with gravity, can you go backwards in time?
All right. I think no.
Okay, tell me why.
Well, only because everything in our observable universe, they talk about the forward arrow of time.
Which is electrons.
Okay.
Or electron.
But like in a simple way in our daily lives, like when I was 10,
Mhm.
that was a age in my life. And then I was 20
That you remember.
that I remember.
Right. How do you remember?
I just think back on,
How do you think back? You recoalesce the electrons at that time in your brain. I can't do that. Only you can do that because you were there and your black hole brain took that information and stored it
stored information.
as a hard drive.
So, okay, so this is a little bit broader than what we're talking. You were talking about like the black hole store information.
Mm-hmm.
Like,
That's all they do. They
and
just
you
take
also
information.
mentioned that, what was that company that hired a black hole expert?
Oh, open AI. Sam Altman hired a a physicist, an astrophysicist for OpenAI,
Who's an expert in black
who's an
holes?
expert in black holes. Why would OpenAI hire a physicist on black hole specialist for AI?
That's I don't know. I mean, it's like the physics of storing information, perhaps, as you're getting at. If you could store
Memories.
information infinitely, I mean, that is really the thing that could. AI runs on data sets. It's kind of getting back to AI in a crazy way.
Yes,
But
it is.
by the way, today, just this morning, I taught a student who was working on making a project in Roblox,
Okay, yeah, it was a video game.
who had Claude AI augmenting his coding. So you tell the AI that you want the game to do something, the AI writes it, and then the game engine does it. I mean, we are in a different age with AI right now.
Yeah,
And
and
it is
the AI is pulling from memory from other places.
Right.
It's like if you had it's like Mother from Aliens. Remember when Sigourney
Yeah, I
Weaver's
do.
is like, Mother, why is this happening? Right? Tell
Right.
me why. And she would give her the information, right?
Right.
And this is what AI, this is my theory
Okay.
about OpenAI and all the data centers and all the Bill Gates and all the stuff. Their plan is to create the brain, the mother brain of AI. And just like with Project Genesis with the White House, they're pulling all those data sets from PNNL, DOE, private organizations, and they're compiling it into Mother to tell Mother, asking, how do we do nuclear fusion? What's the Enigma code?
Right. Super AI solve everything.
Right.
Yeah.
But what they're missing, Jason, is the human element of your own thoughts and your own inquisitiveness and your own memory. I say we've already done nuclear fusion in our prior histories. We just forgot it. In many ancestral way back, we had civilizations that go back to 70,000 to 100,000 years. I think we had that technology back then too. We just made a mistake and we lost it because we annihilated each other, probably. Because that's what happens every time. Every civilization in the universe has to make this one decision. I'm telling you.
Okay.
Because you get to a certain level of technological advancement.
I have a crazy question for you.
Go for it, bro. I mean, they already know the answer. But
I'm going to take this somewhere super crazy.
Star Breeders are talking.
Intergalactic Council. Right?
Bro, yes.
Some people, okay, so let me just get this out. Let me just get this out.
Hit me.
Some people say that there is an intergalactic council of aliens and beings that have contacted us and are basically waiting for us to get our act together.
I would say every species has this problem.
Okay.
Developmental species.
Right. So a bit of a philosophical question. Nothing to do with the science stuff that we've been talking about, but philosophy.
And we can afford that liberty on the show.
Sure. Great. I mean, which is awesome. I mean, let's talk about real stuff in a real way.
Yeah.
That's why I kind of like that kind of freedom of this, because just like two people sitting at a bar having a conversation that goes into somewhere interesting, we're drinking margaritas.
Your lights just came on. You're asking.
Yeah.
Okay, because we have a data set that we can all kind of agree on.
Right.
Now we're going to take another jump and see, does this science kind of fit?
Okay, so my question is that and you and I have talked about this with inventions. Just give me a minute on this one because I got to
build it up.
Okay, so as I told you one time, the guy who invented the Gatling gun, they thought it was going to reduce injuries on the battlefield. They're like, this is great. We got one guy with a gun. We can This is a cowboy and Indian kind of timeline where guns were automated mechanically.
Well, to do one shot, you had to make it took 5 minutes or 4 minutes to make the pellet of lead go in, put the
Right.
powder in, smash it down, cock it, aim it, fire it, and then you got to
Right.
do it again. That was where we're at.
But later they created this thing, the Gatling gun, which was they could mechanically like
Yeah.
and it would fire off shots, machine
12,
gun.
20, 30 shots
Yeah,
at a time.
early machine gun.
Okay.
Then the intent of the invention was to minimize injuries on the battlefield.
Mhm.
Of course, we know that it got used to maximize injuries on the battlefield.
Take out a whole line of folks.
Right. So here we are regarding the Intergalactic Council,
Mhm.
and we show up, humans. They're like, great, you guys are here. You created all this cool stuff. What kind of stuff do you guys bring to the table? And what do we say? Oh, we're a bunch of destruction and, primitive behavior.
Mhm.
Or can we, what is it that do you think philosophically that gets a group of people? Because right now, and I'm not getting into politics, but
Sure.
right now there's a lot of war going on. There's a lot of conflict and strife. There's been that issue, obviously, throughout time. What is it that will allow mankind or humankind
Mhm.
to eventually qualify
Mm.
for, we're not destroying ourselves with our cool technology. We understand it can be helpful or dangerous, and we're willing to behave, and we can show that we're worthy of joining the Intergalactic Council. What do you think about that?
So historically, we just had the Artemis 2 flight break a record going around the moon and being as far out as humanly possible around, away from Earth. And what's interesting is that the Artemis 2 astronauts, they were hugging. There's this really great photo of them hugging each other as they're flying back to Earth. Like they got the glowing blue ball, right? And they're all hugging each other. And they're crew members. And when they came back, they left a message for us when they're up there and saying that basically, in a nutshell, I'm going to basically cliff note this one, that we are alone in space. And the only thing we have, Jason, is planet Earth and ourselves. So we better figure this out. And we better figure it out with love. And we better figure it out now. Because they're coming back from the moon, which is desolate, death. You get out, you blow up, you're gone, you're destroyed. Maybe your spirit energy is gone forever because it's outside the atmosphere and you're floating in emptiness. Now you're a virtual proton of nothingness. So the Intergalactic Council that you speak of is that the humans on this blue dot, this pale blue dot, as Carl Sagan would say it, is we've got to figure out how to work together with our technology as one. And here's the thing. When you have a technology that's based on not finite, but infinite energy potential, right, that is when you go from stage 0 civilization to stage 1. And every species, I think, goes through this pain response where you're a caveman and then you'd have the Industrial Revolution and you have all these things. And then you get to the point of accessing 0-point energy, nuclear fusion, and limitless clean energy for the entire world. Then you begin to understand that you have free will. And if you were an Intergalactic Council and you knew about all this stuff, would you want a monkey coming in with a laser ray gun? No, bro.
Right.
No, dude, no, you stay over there. You're a kid still playing with your gun.
Right.
Ray gun yourself or nuke yourself. When you become spiritually and emotionally well enough to take the step. Because look, Jason, this technology is a small thermonuclear bomb. Every pulse of this thing is a nano black hole. And by the way, the emission spectrum of this thing with our X-ray detectors and our SDD detectors, it has the perfect fingerprint identification of a black hole.
A mathematical signature that is the same as what a black hole emits. Right?
Exactly the same. And it gets even crazier because black holes give us the keys to anti-gravity with eggs. Egg shapes.
Right. Yes.
Check
with
this.
Egg shapes.
Dude.
Like that video I sent you on the thing? Is that why you were saying like, oh my God, why an egg shape?
Egg shapes have a mathematical thing to it. Like we were talking about the Fibonacci spiral. It's totally the key. It's the Enigma key.
There's a lot of sacred math in an egg shape, by the way. A lot.
Like a lot, like
Yeah.
like a whole podcast worth.
So the thing that McCane's talking about is that there's this video, and we'll maybe cue it up on the B-roll
for
here.
Sure.
But the water, this fascinates me when I see this stuff, and I'm sure it is for everybody. The water is going down, like coming out of a faucet, and then if you put an egg in it, the egg will somehow keep getting pulled up and stay in the stream of water.
In the water stream.
It's amazing.
Like an egg.
Why is that happened? What is your take on that? Why is that? How could that possibly be happening?
Well, there's two things. One, there's the vortexing Victor Schauberger.
Okay, yeah, of course, Victor Schauberger.
Thank you, Victor Schauberger.
Yeah.
There's these vortex things that cause a upward action momentarily.
Where?
On the outside, as it's coming down over the surface, it causes a swirl on the surface in all directions.
So there's this upward eddy going around, pulling it up as the water comes. Oh, it's almost the water coming down is fueling it getting pulled up.
Correct. And if you have the UFO with the saucer the demo that we have, when you spin the top of a saucer, just that little electrode on the top, and you spin it, the air goes over the top of the saucer shape automatically.
Right.
And when you do that, the air from the bottom actually comes up too automatically as a byproduct. For every action, there's an equal and opposite reaction. It's just
and by the way, when you say air, that could also be water too.
It could be water. It could be anything. Any type of dielectric medium, even the vacuum of space. Wink, wink.
Yeah.
And so when you use Mother Nature's Fibonacci sequence as a code, you can crack things. Yeah. You can do things that don't make sense.
So when you say the Fibonacci spiral, which it is a spiral, because if you look at the way when it gets mapped out, is that what's happening in the quantum kinetic well?
Mm-hmm.
Is that this is what I think helps make sense. This is how I think of the quantum kinetic well. My understanding of it is that, vibration, you can vibrate atoms, and somehow vibrations done in the right way can make things move together. Like positive, we saw
negative,
in the
positive, negative.
What was that? Something lab?
Actions lab.
Action labs. Yeah, that does that. So it is possible to move. You can emit energy out, but it can move. That can make stuff move in.
As long as you bias it in the right way. Yes.
As long as you bias it in the right way,
or the criteria is met. Yes.
With the frequency and the amplitude, something that would otherwise get pushed out gets pulled in.
It's a phase change. Like when water turns from solid to liquid to gas, it's a phase change.
Huh.
And so when the phase change happens in physics and in electrons and matter fusion, you can cross the boundaries like quantum tunneling. You can make a ball go through a wall.
But that's when but that happens once all of the electrons get pulled closer and closer and closer, so close together. This is the important part, I think. So close together that they fuse because of Heisenberg's uncertainty principle, and they basically occupy the same space, overcoming the Coulomb barrier, and they merge and they fuse, and then that's how you're able to do it without smashing them together with some giant contraption.
A gentle thing. And this is awesome because when you do nuclear fusion, the emission that you get off this thing is ultraviolet, soft X-ray, and medium X-ray, which is 1 keV, 10 keV, and maybe like 0.5 keV or 0.1 keV, which is ultraviolet. Did you know, Jason, that if you have a sperm, right, and an egg, and a sperm swims towards the egg, they found this in science, when the sperm gets into the egg, where it crosses the event horizon, there's a huge glow of ultraviolet radiation, just a huge...
That's so cool.
And then all of a sudden mitosis happens, cell division, split, and then it, for some weird reason, creates a baby with intelligent design, Fibonacci sequencing. What is going on here?
The wonders of nature, the wonders of mathematics, the combination of all that stuff together,
Fusion is love and love is fusion. You don't have to force it. It just happens. Like when you're attracted to a girl, you don't have to try. You just are. And when she's attracted to you, you just are.
Yeah.
Right?
There's definitely a chemistry, as they say, between people when they're meant to be together or meet or whatever.
And to go back to the chemistry of positive and negative charges. like the Hawking radiation of like the electron falling in, information being lost, and then the positron going away into space. And did you know that as the positron's floating away into space, it eventually gets turned into information, like the positron will grab an electron. It's very interesting. But
isn't that destroy it? I thought, help me out with this one, because when you say positron, I think antimatter that's about ready to hit something and get annihilated.
But it lost its counterpart. It lost the ability to explode. That's why the ignition of a black hole never takes place. The ignition of a black hole cannot happen because it's lost its positron information, its quantum entangled boom factor of releasing light, right? Because if you have a full matter-antimatter reaction, it emits a 511 keV gamma ray, which is the most powerful photon in the world.
When you have annihilation.
Yeah, two matter and antimatter hit each other totally and annihilate 100%. It kicks off a 511 keV gamma.
Okay.
Which is very deadly.
Super high frequency.
Deadly.
Ray of energy, right? Yeah.
Deadly.
Okay.
Gamma ray burst, deadly. When a positron floats away and the black hole absorbs the electron, the information's lost. The positron can't detonate because it lost its pair. It's like if you lost your wife. I can't play anymore. I'm sorry. I'm sad. It's like positrons leaving a black hole are sad, in my opinion. They've lost their counterpart. They've lost their lover. And so then they go and try to find a new one, but it's not the same.
And the relationship blows up.
Well, that can happen anytime.
Maybe you have a few too many drinks at the bar and then you make some bad decisions. Is that what we're talking about, kind of?
I would say that a black hole is kind of like that, actually.
Yeah. So
because it's too energetic, like soft voltages of like an egg, like a sperm going into an egg and then creating that ultraviolet. It's a soft fusion. It's the right amount of strings for that oscillation. But if I have only one and it breaks, I've lost it forever, right? I've lost it forever. And now I've got to go start over. It's like an information reboot. Like when you reboot a software package and you're like, I just lost all my hard drive data, dang it, right?
That happened.
I hate it when that happens, right?
That happened, yeah.
It's like, oh, my life, my 2 years is gone, right?
Yes, there was a lot of half-done 3D animation projects that I had to like dig out of the like save file, and you're researching. You're like, I hope this software saves it. But the thing I wanted to sort of dive deeper on regarding the black hole is how it relates to the quantum kinetic well. Because you've said in other podcasts, when it comes to waste remediation, which is what rad waste means, radioactive waste remediation. That you're able to create transmutation of radioactive elements.
Heavy elements. Very heavy.
And process them so they're not radioactive. And you always say you're using time to basically take a half-life of a radioactive element and make it non-radioactive.
Correct.
And I always say to you, but isn't that just you shaking it apart somehow? Is that really time dilation? Well,
let's ask the question, what is time? Let's just go there.
What is time?
What is time, Jason? What determines time? Like, okay, just think about black holes for a second.
Okay.
If I have a photon or even an electron that's flying or being absorbed by the gravity of a black hole, and as that electron's getting closer and closer and closer to the event horizon, time is slowing down.
Okay.
But we know that if I look at an electron and it reflects light back at me in normal mode, normal time is 1 second per 1 second. No gravity. Okay.
In our local environment.
In our local environment, it's 1 for 1.
1 for 1.
And if I get that electron closer to a black hole, now for me it looks like 2 to 1 or 3 to 1.
Wait, say that again. If you do what?
If I make an electron get closer to a black hole, that electron begins to turn black. It starts kind of losing its update function of photon radiation to my eyeballs. I can't see. It's fading out.
Right.
It's disappearing.
Right.
So
Because it's slowing down in time.
It's slow. Yeah. So something about time is closely associated with light.
And gravity.
Well, that's the thing. Gravity is just negative light.
Okay, let's talk about that.
Bam.
That's the one that's the real crazy part. Negative light. I was talking, okay, we mentioned this in the early part of it where we were saying like you turn on a light bulb and we're used to thinking of light as a one-way street. Like
boom.
It emits out.
Like a light bulb. Boom.
Okay. Because, the reason why that is because some electron went in a valence orbit level and emitted a wavelength
Visible
of energy.
Light. Sure.
And that's light.
Yeah, and that goes in your eyeball.
Okay.
And then it goes into your receptors, your cones and rods, and then it gets turned into a signal and goes into your brain.
All of that's great. Now, what's negative light?
Negative light is where the electron or the light gets pulled back towards the emission.
Oh.
Yeah.
Towards the light bulb?
Towards the light bulb. When the gravity is so great, he needs more drink. We're going deep.
Bottoms up on this.
Bottoms up. Now, here's the thing. You probably don't know this, but if you look, now there are 3 types of black holes, Jason. There's 3. 1, there's a retrograde black hole. 2, there's a no rotation black hole. And 3, there's a prograde rotation black hole.
Okay, so let me guess at these guys. Using our temporary object. One is spinning this way, one is spinning that way, and one's not spinning.
In reference to something.
Okay.
The accretion disk.
Okay, the accretion disk, which is that ring of fire around the black hole.
Kind of wanting to start a star, but it's not.
Well, isn't it a star that got basically spooled out?
Well, every accretion disk around. Did you know that Saturn has an accretion disk? It's a Saturn rings. Right, but that's the mechanism of a gravitational flux. It creates. Remember, when you create a negative singularity, you always get a ring.
Interesting.
You always get a ring when you have a gravity flux, and then when you lose the gravity flux, positive light. Everything goes back to normal time.
But also a Taurus.
Mm-hmm. Yeah, Vesica Pisces. Look at that.
Oh, right.
That's
overlapping.
That's a Vesica Pisces,
it is.
bro.
I see it there. Yeah, I see it there. Yeah.
This is the whole secret right here, is a toroidal flux. Huh. Guys, this is it. And it's in the arc reactor. It creates a toroidal Victor Schauberger sucking action to create a gravity and also a time well. And when you get caught in a time well, you have to emit radiation because you're braking, you're slowing down. It's called bremsstrahlung. You're slowing down. The electrons are slowing down. And they're getting sucked into this thing that's changing the timeshare rate of the electron. So whatever time is has to do with electrons and positrons, period. Because remember, if there's no gravity, electron-positron pairs are popping in and out constantly. They're as fast as possible. Totally click, 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 one for one, one for one, one for one. But if the positron-electron pair gets near a gravitational well, they kind of start getting pulled apart. 1, 2 for 1, 3 for 1, 8 for 1, 10 for 1, 20 for 1. The swirling action, you get the steps of the Fibonacci sequence.
Right. That horn shape.
The horn shape happens. And so as it's the time, so basically from this point forward, ladies and gentlemen, time is merely the update function, just like a video game, between positron electron pairs. That's it. That's time. And if there's no disturbance or perturbation, time is fast. And we know this, if we go out in deep space, we age faster where there's no gravity. But if we are on planet Earth, we age slower.
Is there a frame rate that physicists have been able to deduce from that? Like, could you kind of could physicists argue that there is a frame rate and it's this number because we can see how quartz crystals oscillate or some other kind of crystal oscillates, and therefore, or some electron oscillates, you know where I'm going with this? Is there something that gives away what that frame rate is?
Yeah, it's called the microwave background radiation, 1.42 gigahertz. That's the photon. Like if you were to pick on this black body radiator thing, of the spectrum from ultraviolet radiation to blue to green to yellow to orange to red. And by the way, let's just pretend that the red is radio waves, and we'll pretend that the purple is, gamma.
Okay.
So this thing has
spectrum
all the spectrum.
style.
Right. Yeah. There's some spectrum on this electron that determines the degree of freedom of time. Do you know what it is? I just said the answer. It's 1.42 gigahertz. That has to do with the hydrogen electron flip, the Mobius flip of the whole time frame. So when the electron goes from electrostatic update function to a magnetic update function, it has to flip. And then it has to go electrostatic function update to magnetic flip to back to electrostatic field to magnetic field flip, Mobius strip. Okay, this is how the universe works. Even out there in space, it does the same thing. But because the flip is so fast, Planck's constant, it flips really quick, and time is very quick out there. But when you get into a black hole or a planet that has gravity, it can pull it away. That the flipping action happens. There's a time lag. Update function in a video game engine. If you do update function delta change this number, it will slow down the time frame.
Nice job on your Unity code.
I know, right, dude?
I've been doing code. You're writing that code in your mind as you did. Yeah, that is the update function. Yes. Nice
yes, job. And I've also been doing that with the Arduino coding for the Iron Man helmet. It's like literally you just have to use C code to drive the
right.
servo.
Right.
And you have to tell the universe what to do. And it's very interesting. Just to go back to the 3 phases of black holes, as we're getting almost to an hour, we can go another hour, but we do need to close up soon. But I just want one last point, Jason. Retrograde black holes, they spin in opposite directions. The core spins opposite direction to the accretion disk.
Okay.
And what that does to the light emission out is it shifts it towards 6.2 keV iron growth. The mission right here. If you have a no spinning black hole in reference to the accretion disk, you get more of a 3 keV, kind of slides over to like a colder black hole. If you have a prograde that's spinning with the accretion disk, it actually slides all the way down to ultraviolet radiation. So here's the deal. When you have the retrograde where it's spinning opposite direction of the accretion disk, you create a bigger event horizon. It grows bigger. The negative light. This is how UFOs work. Because the top spins one way, and the edge of the craft has something else that spins the opposite way, like an electrode. And so when it spins and pulls down the egg up into the air, it creates more of a negative light.
Interesting, huh?
No, that's how it works.
The spiral, the spinning action of the UFO one way versus the other way.
The retrograde action. Huh. You use astronomy's Enigma codes to engineer your devices.
Yep. Amen to that. There's so many. Nature is the ultimate problem solver of so many of the things that we try to invent, right? There's always something that you can look at and you're like, oh, right. It's a fractal, or it's a Fibonacci spiral, or it's something that you've seen. That's why when we talk about these other inventors, I love that so much, because I honor, we both honor.
We should.
You have to honor the people that have, and the cool thing too is that it may not have been in the subject that you're even in. It could be some other subject that had nothing to do with the thing you're trying to invent, but that had something, gave you some kernel or something some thing to stand on that allowed you to create your next jump.
And all the hot fusion guys, they're just, if you watch them, they're just sitting there going, oh, we're going to do this, we're going to do that, it's going to be great. So this, are they giving any appreciation to any of the forerunners of our past? No, I don't hear any of that.
I think they have business considerations that they're getting funded a lot of money. They've been telling people that it's going to work for 20, 30 years.
80 years.
80 years?
80 years.
That's a little past the deadline. I thought I was taking a long time on my inventions. Shoot, 80
You started
years.
to feel good about yourself.
I'm on time. I guess I'm back on track. I I thought I was a couple of years overdue, but now I feel like I'm on track with that.
Yeah.
But anyways, they're getting all this money. They're putting all this muscle into it. And we talked about this before about the solution for problems. It's easy to take a lot of money and a lot of effort and energy, ironically, and shove it at a problem. A lot of people make their money, their income on this. We've talked about this too, about this griftathon where people are working on some BS project. By the way, can you edit me can you edit out swear words?
The alcohol is talking.
Can you edit out swear words if I turn into some kind of tough guy? No, but I mean, they're making all this money. Everybody's, paying their mortgage with this stuff. You think they're going to mess around with some solution that disrupts all that?
The griftathon.
Yeah.
Okay. That could be a whole podcast in itself,
right.
But I'll just glaze over it so we can, we're over an hour now.
Yeah.
Thanks for bearing with us here. But the griftathon essentially is this thing that has happened historically over years and years and years and years of all of our civilization, from selling apples at a market to whatever, bartering. Okay.
Camels at a bazaar.
You know it.
Yeah.
All the way back to, way beyond our forerunners.
Cavemen. Some caveman was selling.
Here, take my spear.
Yeah.
I'll give you whatever. I want some honey for your spear, that kind of thing. But when you get to this level of technology, Jason, where you can actually access free energy and a lot of it, dangerously amount of it.
Yeah.
Then the bartering system doesn't even matter anymore. And now you have to start recalibrating your systems. Like, this ain't no grift no more. This is like, actually, what is the value of our planetary system? What do we value as a human species on Earth? Do we value life? Do we value death? Do we value money? What is it? We have to start asking these tough questions. What is it that we value, Jason? And for me, as basically a homeless person that basically stumbled on fusion by locking myself in a garage for 7 years, I'll tell you this. My opinion is that we have to find, just like those astronauts from Artemis 2, love. We're teammates. We're comrades. We're whatever you want to call it. Like, we are family on this planet. We got to figure this out right now.
A messed up family, just like every real family. And somebody's got beef with somebody. And it's usually people beef with their neighbors. It's always...
Don't mess with your neighbor, bro.
It's not somebody else. It's somebody who looks exactly like you, but lives a fence across. I mean, isn't that crazy? It's not even like crazy radical racism and stuff. It's people not even getting along with their own neighbors or family members or like people down the street. Like, we can't even do that.
Well, you know why?
Or haven't done that in a great way yet. We have done it. I should say it like this. We've done it in some bits and pieces. We have had some beautiful moments of human development, and we should feel proud of.
So to close on this thought, this is the closing thought, okay. And thank you, Jason, for coming on.
Yeah.
This has been a really fun one.
Yeah. Oh, it's good.
Very special.
Yeah.
But when you go to a church and you go with all your people that you do the sermon with, and you hug and hold hands and you sing in Kumbaya, why does that work? Because everyone agrees on one thing that they can huddle around. And if we can all agree that nuclear fusion is the answer, and it's life and creation and hope and space-time travel and all these great things, and creating materials that save the world.
Yeah.
If we can all agree on that, there's no reason to fight over oil. There's no reason to fight over religion. There's no reason to fight over, my color is better than your color. Bro, we are a multicolored thing.
Absolutely.
Unit of love. And we get to choose. We have free will. We get to choose if it's going to be love or destruction. And I leave that to you, audience, because all we can do here at Quantum Kinetics, and thank you, Jason, and everybody else, is love. Because when you can crack the atom and the electron open to a level that we have discovered, you got to be very careful with it.
Yeah.
Because your next door neighbor is nearby.
Yeah. Yeah. And hopefully we use it all for the best.
Oh,
there's a possibility. I always like to ask this question. I've said this to you too.
Go ahead.
What happens if it all goes well? What's a message of hope if it all goes well? From the guy who invented the ability to do cold nuclear fusion, what is the best outcome of this?
Correction. I didn't discover it. I rediscovered it.
Rediscovered.
This is the rediscovery. Okay. It's been there many years and eons before.
Yeah. As all inventions somehow
correct.
are. Yeah.
It's as we've remembered.
Yeah.
The hope is that we can do anything. We can go anywhere. We can do anything. We can fly. We can do our dreams. And our dreams are beautiful. Or we can have nightmare land. It's that simple. I know what I want. We are showing this every time we come on, and people are like, he's just a stupid kid just playing with toys. No, dude, it's way bigger than that. It's actually a message to you.
Yeah.
Your inner child is a genius. You just forgot. It was killed from you a long time ago by being an adult.
Forgot how to imagine a better outcome or a different possibility.
And I'm going to tell you a little secret that our galactic neighbors are children. They have pure hearts. They don't have any evil in them. They just have love. Because they've already gone through the great lesson. This is the great lesson, guys. And, in 10 years from now, we may have a nuclear blast, nuclear war. At least the message got out. And the choice is yours, not mine. I already know what I'm doing. And I give every day for it.
Yeah.
It's up to you guys. So
That's great.
The torch has been handed to you now. So what are you going to do with it? So thanks so much for coming on the show today, Jason. This was probably one of my more favorite ones because we went a little bit down the black hole road.
We went into it.
And so thank you, everyone, for tuning into the Season 4, Episode 2, First Diffusion. Remember, fusion is love.
Love is fusion.
You don't have to force it.
It just happens.
Bingo. All right, guys, we'll see you on the next one, and have a great rest of your day. Take care.
See you next time.